In this video, we continue on to showing examples of calculating the variance of an estimator. Recall that we denote the estimator beta hat that estimates the parameter beta. Example 1. Let x be from a binomial distribution with parameters n and p. Calculate the variance of p hat equals x bar, the mean of x. So the variance of p hat is the variance of x bar, and x bar is x divided by n. A constant with respect to the random variable x can be taken out of the variance expression but squared, and the variance of a binomial distribution is n times p times 1 minus p. So we have the variance as p times 1 minus p divided by n. Example 2. Let x1 to xn be IID from a Poisson distribution with parameter lambda. Calculate the variance of lambda hat equals the mean of x1 and xn. So you plug in the estimator like in example 1 to calculate the variance of the mean of x1 and xn, and since the x's are independent, the variance of x1 plus xn can be separated into the variance of x1 plus the variance of xn. So we do that and take the 2 out, that becomes 4 in the denominator, and the variance of a Poisson distribution is lambda, and therefore the variance of the estimator is lambda over 2. Example 3. Let x1 to xn be IID from a normal distribution with mean mu and variance sigma squared. Calculate the bias of mu hat, that is the weighted average of the x's, with the weight of the ith term equal to I. In other words, mu hat is 1 times x1 plus 2 times x2 plus plus n times xn over n. We plug in the estimator like always and take I out of the variance expression and have it squared, using the properties of variance. And since the variance of any x is sigma squared, we have the variance as the sum of I squared times sigma squared from I equals 1 to I equals n. Since the sum of I squared from I equals 1 to I equals n is n times n plus 1 times 2n plus 1 over 6. We can further simplify the variance as sigma squared times n plus 1 times 2n plus 1 over n. In the next video, we will show that the mean squared error of an estimator can be derived from its bias and variance and see examples.